next presentation in Chapter 7 is about hypothesis tests, confidence intervals, and multiple regression models. So, in this model, we can test every of these coefficients separately, and in comparison with the simple regression model, there is nothing new, so it is absolutely the same. I will repeat this routine, and afterwards you will see how it looks like when you do the joint test of hypothesis, when you are jointly testing two or even more coefficients. So, on the basis of our OLS method, we can calculate standard error of some of every of our coefficients in the model, and we are expecting that variation of our beta hat in the model is converging toward true value of variance in the population as n grows to infinity, as our sample is growing. And we wish to test the following. So, whether one of those coefficients here is equal to 0 or not. Whether, for example, beta 1 in population is equal to a hypothetical value of beta 1 in population, which is 0. Alternative hypothesis is claiming the opposite, and if we accept the null, then we can say that, for example, for beta 1, if we accept the null, then we can say that x1 variable is not statistically significant. But if we reject the null and accept the alternative hypothesis, then we will say that x1 is significantly influencing y hat, our dependent variable, because beta 1 in population is statistically significant. We can do it in two ways. One is through on the basis of t-distribution. When we calculate t-statistics, we need beta hat from our model, we need hypothetical value which is 0, and we need standard error. So for two-tailed test, if we are only checking if this is equal or different from 0, we will have this relationship with a probability of 95%, so critical value will be 1.96 or something really, really close to that value. And then if t is larger than this critical value, we will reject the null hypothesis. If it is one-tailed test, for example, if we want to check if beta is positive or only positive or only negative in the population, then critical value will be different, and then we will, in the dependency of the sign, we will reject or accept the null hypothesis. When it comes to a confidence interval, it is like you already saw that we need beta coefficient, we need a critical value, we need a standard error in order to conclude the limits in which beta coefficient in population is lower and upper border. So with the probability 95%, critical value is 1.96. If we reduce our probability, then critical value is 1.46. Now let's go to example. Let's do the test score with two independent variables, student-teacher ratio and percentage of English learners. You'll see the standard errors of each of these coefficients here. So we want to check, for example, beta 1 for student-teacher ratio, if it is equal to 0 or not. We will calculate the t-statistics. So beta hat is minus 1.1, hypothetical value beta 0 is 0, standard error is 0.43, so t statistic is minus 2.54 comparing to 1.96. It is or less than 1.96, and p-value less than 0.05, so we will reject the null hypothesis, and we will say that student-teacher ratio is statistically significant in the population. Confidence interval is again the same. We will have the lower and upper limit, and we can say that in population with the probability of 95%, we can expect the beta 1 is inside the limits of minus 3.9 to minus 0.52. So let's go to example how it looks in Gretel. I have already done the model. So you can see student-teacher ratio here, and we already have the t-statistics minus 2.54 for two-tailed test and p-value. So it is less than 0.05. So this is why we know that beta coefficient beta 1 is statistically significant, and student-teacher ratio is statistically significant, and it's influencing our test scores. When it comes to confidence intervals, analysis, confidence intervals for coefficients, and we will have the limits for all our coefficients in the model. In this example for student-teacher ratio, beta 1, these are the limits for the probability of 95%. Okay, let's go to the next example with the theory actually. So now we are going to joint hypothesis testing. For example, if we want to calculate what is the effect of student-teacher ratio and test scores holding the expenditure per student constant. Now, you see here that we have one more variable in the independent variable on model, and this is the expenditure per student. But what is going on? It looks like, and you will see very soon in the model, the student-teacher ratio does not have effects on test score because it is not statistically significant all of a sudden when we have imported one more variable in our equation. But we also see that correlation between student-teacher ratio and expenditure is significant. It is really, really high. It is negative and it is 0.62. So let's do that also in our model, in Gretel. Now we will develop model 2, ordinary squares, so test scores, and we need expenditure per student to add in our model. We'll do robust standard errors. And you see in this model, model number 2, the student-teacher ratio all of a sudden is not statistically significant, but expenditure per student is statistically significant. We can do also correlation to check for these two variables. So student-teacher ratio and expenditure per student, right-click, correlation matrix. And we can see it is minus 0.62, like I said in presentation. So obviously it is very, very high. What we can do in that case? We need to do joint hypothesis testing because individual tests are not correct, because we already talked about the problem of multicollinearity, that software is not capable of dividing the influence of student-teacher ratio on test scores from the influence of expenditure per student, expenditure per district on test scores. We actually want to do the following. We will test them jointly. So beta 1 and beta 2, we will test if they are equal to 0. Actually, two coefficients we will test altogether. We actually now have two restrictions on our model because we have included in our hypothesis two coefficients. So if we compare unrestricted model, so this is the whole model where we have all three independent variables with coefficients. And if we impose this hypothesis, we actually have two restrictions. We are losing this element here, beta 1, and this element here, beta 2. And now we have our unrestricted model without these two coefficients. Number of coefficients is marked by the symbol Q, and in this case it is 2. We need to tell the computer package which restrictions to apply in order to calculate the significance, and it is not straightforward work. We need to know how to write it in Gretel. So when we are doing with heteroscedastic robust F statistic, like we did in this example, you remember that I marked heteroscedastic robust errors, then we will calculate F statistics, which has the distribution of Snedeker F distribution, where it is actually calculated on the basis of the number of restrictions, and it is for the large sample approximation. F statistics will be compared to critical value, and then also we can calculate p-value. And if the case is that f statistics is higher than critical value and p is lower than level of significance, we will reject the null, saying that at least one of betas is different from 0. This value we can find in the statistical table for F distribution, or we can use the option in Gretel to find it also. But we will have p-value anyway. So let's talk about a little bit more about the overall regression of F statistics. It is F statistics. This is something different. I will show you in the model where it is. Let's go to model number 2. So this is the model where we have three independent variables. This is F statistic. This is the p-value for F statistic. It is not F statistic that we use for testing joint hypothesis. It is F statistics for significance of the entire model of all independent variables as a group. So, in our model, we are actually making the hypothesis that all our coefficients are equal to 0, or alternative that at least one of them is not equal to 0. So this is our overall F statistic. The goal of this testing is to answer the question, do the x's as a group, do our independent variables as a group are explaining y? If we have only one restriction, it goes like this, if bb equal to 2 to t statistic, but in this case, we have as many restrictions as we have as many independent variables or coefficients. So let's just go back to our example to comment on this. So I already said it is here, p-value for F statistics. It is really low because it has 65 zeros before the first number. So it is less than 0.01 or 0.05 level of significance. We can conclude that independent variables in our model as a group are statistically significant, and that as a group they are influencing our dependent variable. Now, let's go back to joint hypothesis testing. So we had this example where student-teacher ratio is not statistically significant, but expenditure, yes. It can be that both those variables are not statistically significant, but together they maybe are. So this is why we need to test them. So we will make the hypothesis like this, that beta for student-teacher ratio, beta 1, is equal to beta 2 for expenditure, and they are equal to 0. So we have two restrictions. Alternative, if we reject the null, that one of these two coefficients in population is different from 0. So on the basis of joint hypothesis, we will calculate the F statistic is 5.43. From table, critical value for 95% is 3, for 99% is 461. So we will reject the null, saying that at least one of these two coefficients are different from 0. So jointly, actually, these two coefficients are statistically significant. How do we do these restrictions and testing in our example? Let's go back to model number 2. So we will open option test in model not in the general menu, but in the menu for the model test linear restrictions, and we will write down here our restrictions. You need to be careful with the syntax, so you can use help to see how syntax goes here in Gretel. So I will take this part. I'll like to do it this way, so to copy it, and then saying that beta 2 is b2 is equal to 0, and in second row b4 is equals to 0. So why b2 and b4? Because Gretel goes like this. So constant is b1, student-teacher ratio is b2, English percentage of learners, percentage of English learners is B3 and expenditure is B4. So if we are testing the equality of student-teacher ratio and expenditure, so we are actually testing whether B2 is equal to 0 and B4 is equal to 0. When you click OK, you will get the results. So the same value like you saw in the example in PowerPoint. So F statistic is 5.4, p-value 0.004, so it is less than 0.01 level of significance, or 0.05. So we can say that at least one of these two coefficients is statistically significant and different from 0 in the population. Here you see the results of restricted model without these two coefficients. So this is how it goes in Gretel. In the case if you have schemoscedastic data, so you don't have the problem with heteroscedasticity, F-test can be obtained from two regressions, so it can be obtained on one easier way. So for example, if we have this model and we want to test if beta 1 and beta 2 are equal to 0, this is our restricted model. So we have again Q is 2, number of restrictions. We can run unrestricted model and save this sum of square residuals and also do that for the restricted model. And then we can calculate F and compare it with the critical value of F. Other formula is also this one, where you are using actually R squared to do that. But you can use this formula only if you have homoscedastic data. So n is small, you have homoscedastic data, and you have normality of your residuals. So this is how you use that critical value. Let's go to our example. Let's assume that we have homoscedastic data and we want to repeat the previous procedure, but this time it will be with homoscedastic case. So we are again testing the same hypothesis, whether these two coefficients are equal to 0. These are the R squared for unrestricted and restricted models, and our F statistic is 8.01, while critical value is 4.61, and again 80 is rejected. How we can do that in our model in Gretel? So we need to develop third model, model number 3, but it has to be homoscedastic. So model, order least square, we already have everything here, but this time we won't mark this, because if you mark this, then you will have heteroscedastic model that is heteroscedastically robust. But in this case, we have homoscedastic model. This is why we will leave as it is, without marking it. If we click OK, so you see that in comparison to model number 2, we will get a little bit different, coefficients. So this is model 2, this is model 3. Well, actually, almost the same. But anyway, standard errors are calculated differently. You can see that, for example, standard error for beta 0, this is homoscedastic model, this is heteroscedastic model. They are a little bit different. But now we are doing the test, joint hypothesis testing, in the homoscedastic case. So model number 3, test, leader restrictions, the same restrictions as we had before, that B2, actually in our case beta 1 is equal to 0, and B4, in our case beta 4 is equal to 0. Okay, and here it is. Now we have F statistic 8.01 and p-value is really, really low. Now again, we will reject the null hypothesis. So this is how it goes if you have homoscedastic case. Testing a single restriction involving multiple coefficients. This is the case that we will do only theoretically. That, for example, beta 1 are equal to beta 2, and for example, that beta 1 plus beta 2 are equal to 1, or even more complex hypothesis, then it goes to two approaches. You can put the restriction in software if software allows. We can do that in Gretel. Or the other one is to rewrite the model in order to restrictions appear as coefficients. For example, if we have this model, and this is our hypothesis that we want to test, we need to add and subtract beta 2 x1 in our equation, and then when we transform it, I'll do this quickly, we will actually get the new model. So actually gamma is beta 1 minus beta 2, while on the other side, beta 2 times the two variables, x1 minus x2. And now what we have to do is just testing if gamma is equal to 0 or not. So instead of this, we will test this, as this is the new coefficient, and then if it is equal to 0, beta 1 and beta 2 are actually equal to 0. If there are more than one restrictions, then it's getting more and more complex, but it is the same approach that you need to know algebra a little bit better, and then to implement these restrictions in the model, and then develop a new equation with the entire restriction in one coefficient. Homoscedastic case, the same as before. So we have these two restrictions, beta 1 plus beta 2 are equal to 2, beta 2 plus beta 3 are equal to 3. And when we transform this equation, we will actually get this formula. We have some new equation, and we will test if beta 2 is actually equal to 0. We will get F statistics and then saying compare it to the critical test. So this is about joint hypothesis. We will do the simple way. We will do only the case where certain coefficients are equal to 0, or maybe 2 of them or 3 of them are equal to 0 jointly, maybe equal to some other value, or larger than 0 or lower than 0, and this is it. We will not develop complex hypotheses. Next chapter is about confidence sets for multiple coefficients. So this is our model, and we want to develop confidence interval for joint hypotheses. We cannot have only two limits for one beta coefficient, because we have now two or even more coefficients. So we need to make ellipse if we have two coefficients, because we will have entire area on the graph showing us in which part of the graph we can expect the values of our beta 1 and beta 2 coefficients in this case. For example, we already rejected the null that beta for student-teacher ratio and beta 2 for expenditure are equal to 0. And now if you want to test it, we will actually get this sphere showing us that where is the true value of our beta coefficients if they are crossed. So this is values for coefficient on student-teacher ratio beta 1. This is the values for the coefficient of beta 2 for expenditure. Their value, true value in a sample is here, that we can expect with the probability of 95% that true value of beta 1 and beta 2 coefficients in the population can be in this area. So maybe it can be beta 1, it can be maybe -1, and then maybe beta 2 can be only 0.8, somewhere here, for example. So how it goes in Gretel? I will do it on the model number 2. So analysis, confidence ellipse. I need to put on the right hand side window for which coefficients I want to calculate this surface. So for student-teacher ratio and expenditure. And when I click on OK, so this is the surface. And this is the sphere actually, where we can expect the true value of beta 1 and beta 2 coefficients in the populations. in the one population. Okay, so with this graph, this is actually the end of this presentation.